Okay. So I'm going to start the second portion of the talk. So this one is going to be on secretary problems instead. And just again, to give you a heads up, the format of the talk will be similar to the first half, where I am going to show you complete proofs of things. The technical detail will be roughly comparable to the first half. Okay, so we already saw motivation from the first half. Let me just remind you of what the secretary problem is in the model here before I get started. Okay, so what's going to happen is offline, every secretary is going to be assigned a weight by an adversary. This is unknown to you. The secretaries are going to be permuted randomly. And then online, the secretaries are revealed to you one at a time. Once it's revealed, you learn their weight, and you have to immediately and irrevocably decide whether or not to hire. And your goal is to maximize the probability of selecting the max weight element. Okay, so just again to show you this animation of what this might look like is here the adversary has assigned some weights, and then they're going to be revealed in some random order, and you're going to decide to accept or reject. So say you decide to reject, and then you decide to reject again, and then when you finally decide to accept, you have to do this again without learning what's going to happen in the future. Okay, so again, I'm just going to go even quicker straight into some analysis. The first part is going to be more basic. It'll get a little bit more difficult as we go throughout the talk. Okay, so let's first try and reason about what does the optimal policy look like. So first, let's observe that the optimal policy, without loss of generality, only accepts elements that have the largest weight seen so far. Okay, so why is this? Well, any element that isn't the largest so far is clearly not the largest element of the entire set. So you don't gain anything by accepting it, and maybe if you reject it, you get something in the future. Okay, and the second observation I want to make is similar to profit inequalities. You can find the optimal policy using dynamic programming and backwards induction. Okay, so let's try and reason through this. So if somehow we make it to the very last element, and it happens to be the largest so far, then of course we should accept it, because it's actually, we know it's the largest element because it's the last element in the set, and we have nothing to gain by rejecting it. Okay, so let's go one step back. And let's say if we make it to step n-1, and we see the largest element so far at step n-1, what are our two choices? We can either accept it, and then as long as the real largest element isn't coming in the next step, this is actually the largest element of the entire sequence. And that happens with probability 1 minus 1 over n. Right? So as long as the last element doesn't happen to come at the very last step, then if the n minus first element is the largest so far, it is actually the largest element of the whole sequence. Okay? So if you accept it, you get the largest element with probability 1 minus 1 over n. If you reject it, then you're going to reach the last element, and that one will be the largest only if the largest element winds up arriving at step n, which happens with probability 1 over n. Okay, so as long as n is at least 2, it's at least as good to accept n minus 1 instead of reject. Okay, and we can repeat this reasoning further backwards and say if we make it to step I, and we see the largest element so far, what are our choices? We can accept it, and then we get the largest element with probability I over n. So why is this? So as long as the largest element comes in the first I steps, then conditioned on I being the largest element so far, it is actually the largest element of the whole sequence. Okay? Or we can reject it, And then we don't necessarily get the largest element with probability n minus I over n, because maybe the optimal policy can't guarantee to get the largest element just because it shows up later. But let's just denote this by f of in to be the probability that the optimal policy selects the largest element conditioned on starting from step I plus 1. Okay, so these are probabilities that we can compute using backwards induction, and we should accept element I if and only if I over n is larger than f of in. Okay, so all this observation is saying is that you can use dynamic programming to find the optimal policy. And I left part of the proof up here because I want to do some reasoning about these probabilities f of in. Okay, so the next observation is that if I is less than j, then I claim that f of in is at least as large as f of jn. Okay, so let's prove this. So one policy that I can use starting from I plus 1 is I could just reject everything until I reach step j plus 1, and then run the optimal policy starting from j plus 1. Okay, and this will succeed with exactly probability f of jn, but maybe there's something better I can do starting from I plus 1 than decide ahead of time I'm going to reach j plus 1. Okay, so this means, just to parse what this means, is that for earlier indices, you are more likely to find the optimal element after it than you are to find the optimal element after a later index. So this should intuitively make some sense. Okay, and the last observation I want to make, and this is the key one that I'm going to keep after this slide, is that now we can say much more about the optimal policy than just that we can find it by solving a dynamic program. That the optimal policy has this following simple format. It's going to set some cutoff time, t. It will reject everything before time t, and it will accept any element after t if and only if it's the highest element we saw so far. Okay, so why is this? So we learned from observation 2 that the optimal policy accepts I if and only if I over n exceeds this f of in that we computed, and it's the highest so far. Okay, so now if I is less than j, and the optimal policy would accept I, conditioned on being the highest so far, we get the following chain of inequalities using observation 3. So j over n is certainly larger than I over n. Because the optimal policy would accept I over n is at least as large as f of in. And by observation 3, f of in is at least as large as f of jn. Okay, so in the outer two directly say that the optimal policy would also accept j if it was the highest so far. So this means that whatever the minimum time step is that the optimal policy would accept I, conditioned on being the highest so far, it will also accept anything after I, conditioned on being the highest so far. Okay, so this is the only observation I want to keep from the previous slide. And now I want to find what is the optimal choice of cutoff. So what is the optimal policy? Okay, so before we do that, I want to give you a suboptimal choice of threshold that basically, it's as a cute, simple proof, and the idea will actually be useful later. Okay, so I claim that there is a choice of cutoffs that guarantees selecting the max weight element with probability at least a fourth. Okay, so what is that policy? So let me read this bullet first. So really what you would like to do is you would like to have every element come before the cutoff with probability a half, and after the cutoff with probability a half. And you'd like this to be independent of where the other elements wind up. Okay, so how can you simulate this by choosing a cutoff? Well, you can choose a random cutoff from the binomial distribution n1/2. So formally I mean flip n coins that are unbiased, and the number of heads, set that to be your random cutoff. Okay, and this has the property that every element is before the cutoff with probability a half, independent of the other ones, because our ordering is uniformly at random. Okay, so now let's reason that if the highest element comes after our cutoff, and the second highest element comes before the cutoff, we will definitely select the highest element. So why is this? The second highest element comes before the cutoff, so it will definitely be rejected. Everything that comes before it will also be rejected. And anything that comes after it has to be larger than the second highest element to be accepted. and only the highest element is. So we will definitely have room for the highest element. And when the highest element comes, it will be after the cutoff, so we will choose to accept it. Okay, and the above occurs with probability of fourth exactly because the highest element comes after t with probability of half, and independently, the second highest comes before t. Okay, so this is just a cute proof that you can get a fourth. This isn't optimal. And actually, the best you can do is due to a seminal theorem of Dynkin, which shows that the optimal policy gets the highest element with probability roughly 1 over e. Okay, so let me prove this. And there's going to be one lemma and one corollary of this lemma. Okay, so what we'd like to do is figure out first, for any time step little t, what is the probability that we have not accepted something before we reach time step little t? Okay, and I'm claiming that if we use cutoff big T, that this is exactly the probability. It's the min of our cutoff over t and 1. Okay, so let's prove this. So certainly, if little t is less than our cutoff, we will definitely reach time t, because we won't accept anything before the cutoff. If instead little t is after the cutoff, then we reach it if and only if no element between our cutoff and t is the highest so far. So if and only if we don't accept anything before we get there. And let's see about what has to happen for this condition. Okay, so I claim this happens if and only if the highest element from the first t time steps also arrives before the cutoff. Okay, so let's see why that's the case. Let's say x is the highest element from the first t time steps. If it happens to come after the cutoff, it will definitely be accepted. Okay, so because it's the highest element from the first little t time steps, it's definitely the highest that has been seen so far when it arrives, so it will be accepted. If instead it arrives before the cutoff, it will definitely be rejected. Everything that came before it will be rejected. And everything that comes in between the cutoff and little t can't be accepted because they all have weight less than x. Okay, so we reach time step little t if and only if x arrives before big T. And this probability is exactly the cutoff over little t. Okay, because this is it's just a function of the ordering of the elements that come before t. It has nothing to do with what those elements actually are, which element is arriving at t, it doesn't matter. It's just a property of how they're ordered. Okay, and the ordering is uniformly at random. Okay, so that's the lemma. So what's the corollary? Is that now we can compute for any cutoff time what is the probability that it selects the max weight element. Okay, and I claim it's exactly this sum, which is just summing over every time step that the highest element might arrive at and possibly be accepted of this term, which is just the cutoff over little tn. Okay, so let's prove this. So the probability that we select the max weight element just sums over every time step the probability that the highest element arrives at that time step and is selected. Okay, if little t is less than our cutoff and the highest element arrives at time t, it definitely isn't selected, so this term will be 0. If instead it arrives after the cutoff, then it's selected if and only if we have not accepted something before reaching there, so if and only if we reach that time step. Okay, but we worked out in the lemma exactly what this probability is. So, so we worked out exactly what that probability is. And now we just need to observe that this is independent of whether or not the highest element arrives at that time step. Because again, whether or not we reach time t is only a property of how the elements before time t are ordered. It is not a property of what those elements actually are. Okay, so this means that the probability that we select the highest element is exactly what we said. It just sums over every time step. This 1 over n is the probability that the highest element arrives at time step t. And this big T over little t is from here the probability that we actually reach that cutoff. Okay, so this is the corollary. And with these two, we can now prove the theorem. Okay, and basically all we're going to do is we're going to try and optimize this sum over all choices of cutoffs. And all that happens here is we observe that for very large n, this sum is approximately the same as this integral. We can evaluate this integral. It happens to be the cutoff over n times the log of n over the cutoff. And then we can take a derivative and find out that it's maximized at exactly n over e, which gives us a success probability of 1 over e. Okay, so that's a complete proof. Are there any questions about this? Okay, good. Okay, so that's the optimal policy, and this is due to seminal work of Dinkin. And I will also just point out that if instead your game is not to maximize the probability of selecting the heaviest element, you want to maximize the expected weight of the element you get, then you can see that this is also at least the max weight element over E, right? Because you select the max weight element with probability 1 over E, maybe you select something else the remainder of the time, and that gives you only additional. Okay, so before I go on, so we are going to go into multiple choice problems again in this talk. Before I do that, let me just compare to the single choice profit inequality. So in both cases, there is a simple policy that gets a constant and optimal competitive ratio. In the secretary problem, we had to do some extra work, but we were able to show that this simple policy is actually optimal on all instances. Okay, it's not that it just gets the optimal competitive ratio, it's actually the optimal policy. Whereas in the profit inequalities, the simple policy does get the optimal competitive ratio, but it's not necessarily optimal on every instance, right? So the dynamic program there gave us something more complex as the optimal policy. Okay, so that's everything I'm going to say about the, yeah.
If you can return to the previous slide. So do you know that the 1 over E is also tight for the case, for the Gabler problem? I mean, if you want to maximize the, I mean,
yeah, so
it's tight, but
it is tight. So just imagine, so I mean, okay, so there are no distributions, right? So you don't know anything. So really just imagine that all the weights are, you know, like 1,000,000 to the I. You have no idea, you know, what I is or where they start. There's really nothing you can do, yeah.
Still it needs formal proof.
That's right. So I'm not claiming that this is a formal proof, but I like.
There is a formal proof.
Okay, so there is a formal proof. I just don't know it, and it's not written on the slides. Yeah. Thanks. Okay, so and the rest of the talk, again, we're going to look at multiple choice secretary problems. Okay, so it generalizes exactly the same way as profit inequalities. Let me just state it to be clear. So offline, what's going to happen is every secretary is going to be assigned a weight chosen by an adversary. The adversary, in addition, chooses some feasibility constraints, which is which secretaries can you simultaneously hire, and then the secretaries are permuted randomly. Online, the secretaries are revealed one at a time. You interview and learn their weight. You immediately and irrevocably decide whether or not to hire. And again, the game is that you must maintain your set of hires to be feasible at all times. Okay, and now when I'm phrasing it like this, I will change the objective to sound just a little bit different, and we'll say you want to maximize the expected weight of your hires. Okay, but just remember there are no distributions here, so the expected weight is over the randomness in the permutation, but you're always going to try to compete with the max over all feasible sets of the sum of weights in that set. Okay, so you're not competing. What you're trying to compete with is not a random variable. It's fixed because the adversary chooses the weights and they're fixed. There's no randomness there. Okay, so again, this slide is supposed to serve the same role as in the previous talk. I will leave it up and talk for a minute or so. I'm not going to read through any in detail. It's again just to show you that there's been a lot of recent work from our community on multiple choice secretary problems. Okay, so while it's up.
Sorry, just one thing that I mentioned. So the first one actually is our paper, so this is wrong. The first paper is the paper of, Bobby Weinberg, me and David Parks. That's the time that we are introducing the secretary problem for the auctions. And all others are just follow-up of that work, given the first
I see. So I didn't know that. So it's still it's the same ratio.
No, I mean, that's for the K version that we said that this K version has application essentially in auction design because you want to select essentially sell K items. And that is the paper in EC 2004 essentially.
I see. And it's the same competitive ratio?
I mean, he improved the ratio, but I mean, we don't get such a ratio.
Oh, I see. Okay.
I mean, introduce the whole thing essentially and say that the application for that one. That's Kleinberg, Parks, and me, EC 2004.
Okay. All right. Thanks. Okay, so let me, I'll just define some terms for you. These terms actually aren't going to be used later in the talk, but I figured I should say something while this slide is up, and these are useful terms to know the definitions of. Okay, so a transversal matroid is one type of feasibility constraints where the elements are left-hand nodes of a bipartite graph, and the set of nodes is feasible if and only if there exists, basically if and only if it's possible to match every node in this set to a distinct right-hand node. Okay, so it's not quite bipartite matchings, but it's basically one side of a bipartite matching, and it happens to form a matroid. Okay, a regular matroid is the following kind of odd definition. So if it is possible for every field F to represent your elements as vectors in a vector space over F, such that feasible sets correspond exactly to linearly independent subsets, then the matroid is said to be regular. Okay, so these are special kinds of vector spaces that can be represented over every field, not just one. Okay, but again, this is all I'm gonna say about these results. And okay, and before I get in, so I am going to prove some results, but before I do that, I actually am going to use a little bit of terminology from matroids throughout this talk. Everything I'm going to use is pretty basic and will fit on this slide, but I just need to go through it first. Okay, so just to remind you, a matroid is feasibility constraints that are first downwards closed, and second, they have this augmentation property that whenever two sets are feasible and one is larger than the other, there exists an element in the larger one that you can add to the smaller one that maintains feasibility. Okay, I'm also going to use this term, the rank of a matroid, which is the maximum size of any feasible subset of, the rank of a set is the maximum size of any feasible subset of S. Okay, and again, if this is a little bit abstract, you should think of vector spaces. You would say the rank of a vector space is the maximum number of linearly independent vectors contained in that space. Okay. So with this, feasible sets are exactly the ones that have their size equal to their rank, and that you can read that from the definition. And we sometimes also use this term basis of a set S to be any subset that is feasible and has size equal to the rank of S. Okay, and this term is also drawn from linear algebra, where you would say a basis for a vector space is exactly the same thing. Okay, I'll also use this term, the span of a set, which is formally all of the elements such that you could add them to S without increasing the rank. Okay, and again, you should intuitively think of vector spaces. You would say the span of vectors is everything you can write as a linear combination of them. And if you were to add them to this set, you would not make the basis any larger. Okay, and the last fact I'm going to use is a theorem from Edmonds. I'm not going to prove this or anything. Many of you probably know this already, is that the greedy algorithm finds the max weight feasible set in all matroids. Okay, so what is the greedy algorithm? It means that if you sort the elements in decreasing order of weight, and you just run through them and accept any feasible element, this will find you the max weight basis of any matroid. Okay, two other facts that are true is first, that it's feasible to accept I when you go through this, if and only if I is not in the span of the earlier elements. Okay, so you should think about this. One example of matroids are acyclic subgraphs of a graph. And we know that the greedy algorithm works to find a min or max weight spanning tree. And you can think of elements being spanned if adding them would form a cycle. Okay, so this is again just to try and draw intuition for this. And what this implies is that I is in the max weight basis if and only if it is not spanned by elements that are heavier than it. Okay, so I am going to use this terminology and some of these facts later in the talk. Okay, so what am I going to do in the rest of the talk? So I just want to give you a taste for some of the different techniques that people use to prove multiple choice profit inequalities. And I'm going to do it with these three results. And I do want to point out that I'm not going to use any deep or interesting matroid theory in this talk. There are some results that use real matroid theory comparable to the kinds of theorems we have about linear algebra, there exist similar theorems for matroids, and there are some papers that use them, but these are really going to be more first principles types arguments, and they're not going to use anything more than what was on the previous slide. Okay, so now I'm just going to get in. I'm just going to prove these three results, and that will be the rest of the talk. Okay, so this is a theorem due to Babayoff and Morlicka, Kempe, and Kleinberg that shows that there is an E approximation for K-uniform matroids. Okay, so what is the algorithm? So when the element at time step t is processed, you're going to do the following. So if the time step is too early, so if it's less than n over e, you reject it. If the current element is not in the top k so far, then reject it. This third condition is a little bit weird. I'll give you some pictures to explain it. Is if the previous kth highest element before you arrived comes after the cutoff n over e, then you also reject it. Okay, so this is going to seem, this is a little bit of a weird condition, and the intuition for why this is a good idea comes from the proof. So just hold off on expecting intuition, and let me just at least give you some pictures to show you what this algorithm is actually doing. Okay, so here's an example where k equals 2 and n equals 5, and just to make this example valid for the algorithm, pretend that the cutoff is 2. Okay, so 5 over e is less than 2, the cutoff should be 1. I'm using a cutoff of 2. Okay, so what's going to happen is when Bulbasaur comes, Bulbasaur is before the cutoff, so Bulbasaur will be rejected by this. When Squirtle comes, Squirtle is before the cutoff, so Squirtle will be rejected. When Charmander comes, Charmander is after the cutoff, so that's good. Charmander is in the current top 2 so far. And what is the previous second highest element? That's Bulbasaur. Bulbasaur arrived before the cutoff, so we will accept Charmander. Okay, when Pikachu comes after the cutoff, so that's good. He is in the top 2 so far, so that's good. And what is the previous second highest element? So the previous second highest element was Squirtle. Squirtle came before the cutoff, so we will accept Pikachu. Now when Mewtwo comes, Mewtwo is after the cutoff. It is in the top 2 so far. The previous second highest element, though, is Charmander. And Charmander came after the cutoff, so the algorithm will choose to reject Mewtwo. Okay, so this is one run of the algorithm. I'm just going to show you 2 more pictures to make sure it's really clear. Okay, so again, the first 2 elements will always be rejected because they come before the cutoff. Any element after the cutoff, so Charmander is in the top 2 so far, and the previous second highest element is Squirtle. So, and Squirtle came before the cutoff, so we'll accept Charmander. When Bulbasaur comes, it is after the cutoff, but it's not in the highest 2 so far, so we'll reject. Now when Mewtwo comes, it is in the top 2 so far, but the previous kth highest element is Charmander. So before Mewtwo came, the top 2 were Pikachu and Charmander. And Charmander came after the cutoff, so this rule will say reject Mewtwo. Yeah.
So basically when the third condition holds, you just stop, right? You're not going to accept anyone.
When the third condition holds, no, because
how can it reverse?
so let me see if
Yeah, because the k
you can get a new you can get a new kth highest.
But then it's between n over e and t.
So in the off chance that the k minus 1 highest.
Yes, that's a better
And then the k highest comes.
yeah.
I see.
Yeah. Good. Thank you.
Sorry, can you please repeat his answer?
Yeah, so he said, so what might happen is that currently the kth highest is after the cutoff. Then a new element comes that is the new k minus first highest. And maybe the previous k minus first highest was before the cutoff. So now the kth highest will get pushed down to be being before the cutoff. Yeah, thank you. Okay, good. And the last example I wanted to run, okay, so the first 2, Bulbasaur and Mewtwo, will be rejected. They're before the cutoff. Squirtle comes. The current element, it is in the top 2 so far. The previous second highest was Bulbasaur, so Squirtle gets accepted. Charmander comes. It is in the top 2 so far, but the previous second highest is Squirtle, which was after the cutoff, so Charmander is rejected. When Pikachu comes, it is in the top 2 so far, The previous second highest was Charmander, who came after the cutoff, so Pikachu is also rejected. Okay, so does the algorithm make sense? This is not supposed to give you intuition as to why the algorithm is good. This is just supposed to show you what the algorithm is doing.
Stupid question, probably. Is it clear that we'll pick only K?
That's the next. The next thing I'm going to say. So it shouldn't be clear, but it will be now. Yeah. Okay. Okay. So the first observation is that the algorithm will never accept more than K elements. Okay. So why is this? So let's let S be the top K elements that arrive before the cutoff, n over e. And now we can kind of see that every element we accept kicks out one of these elements from being in the top K. So every time we accept something, we can map it uniquely to an element in S. And so this means that we can never accept more than K elements because we only had K elements in S to start with. Okay, so there's a charging argument that says we don't accept more than K. Okay, so that's good. So it at least means that this algorithm is feasible. Now we need to show that it gets a good approximation. Okay, and in the proof of this proposition, it'll become clear why we wanted to have this weird rule for accepting and rejecting. Okay, so if I is in the top K, then the true top K, so it's really one of the top K elements, it is definitely in the top K so far when it arrives. So it will always pass this second test. And if it arrives at a time step after n over e, it'll pass the first test. So it gets accepted if and only if the kth highest element from the previous steps arrive before n over e. Okay, because it needs to pass the third test. Okay, and the probability that this occurs, this is very similar to the reasoning from the one uniform case, is exactly n over e over t. Right? Because where the kth highest element from the previous steps arrives is only a property of the ordering of those elements. It doesn't matter what those elements are. It doesn't matter what element is arriving at time t. This is only a property of how those elements are ordered. And because the ordering is chosen uniformly at random, the probability that this specific element happens to fall before the cutoff of n over e is exactly n over e over t. Okay, yes?
T minus 1.
It should be, yes, sorry. It should be t minus 1. That's right. So subject to this being, so this should be t minus 1, this should be t minus 1. I'll keep this one as t. Okay, so now this math is exactly the same math that we saw for the one uniform case. Okay, so the probability that element I is accepted, conditioned on being in the true top K, sums over every index after n over e, the probability that it arrives at this index, which is 1 over n, times n over e over t, the probability that it gets accepted, conditioned on arriving at that index. This is, again, approximated by this integral, and this integrates to exactly 1 over e. Okay, so the whole reason for using this weird rule was we wanted to make the math look exactly like the one uniform case and pick a specific element and say if this element happens to come before the cutoff, then we get accepted. If it happens to come after the cutoff, then we don't get accepted. Okay, so this is, I guess I'm just going to say one more thing. Oh, sorry. Okay, so now that we have this observation and proposition, there's just one more line to finish up the proof. Basically, the observation guarantees that the algorithm is feasible, and the proposition guarantees that we get an E approximation. Okay, so this is the whole proof. Are there any questions about this? Yes?
So if you don't have that condition, is it known that the algorithm...
If you don't have this condition, the algorithm does work. The proof is much messier. So I think this is, without this line, I think was in the original like Babayoff and Morlicka Kleinberg paper. And then they have a follow-up with David Kempe that provides this modification, and the proof is much cleaner. So that's why I wanted to present this one. So even though the algorithm is a little messier, the proof is like way cleaner to do it this way.
Is the E tight?
E is not tight. It's not. It's like 1 plus order 1 over root k, and that is asymptotically tight. So for k, so as k grows, you can do better and better and better. Okay. So what I want to point out about this, there is an underlying technique that might generalize beyond just k uniform. So what happened was we took these samples to be the max weight feasible set of elements that came before our cutoff. And we decided that whenever we accept an element, we're going to charge it to one of the samples. And we found out how to do this in a consistent way so that no sample is charged twice. Excuse me, and the samples are charged consistently to maintain feasibility of the accepted elements. Okay, so this is a kind of idea that possibly could generalize beyond just K-uniform matroids. And that's everything I want to say about this theorem. I'm going to move on to a new result after. Okay? Okay, so the second result I want to show you is for graphic matroids. Okay, so here this is a result due to Karula and Paul, that there's a 2E approximation for graphic matroids. Okay, so let me state the algorithm, and again I'll show you in pictures what's going on. So you're going to pick a random ordering of the nodes offline, and then you're going to define the following sets. For every node V, take all of the edges that have one endpoint in V and the other endpoint later than V in the ordering. Okay, and call this set E sub V. And now you just run Dinkin's one uniform algorithm on each E sub V separately online. Okay, so what does this look like? So here's as an example. Let's say that this is the random ordering you choose. The lower nodes come first. Then what's going to happen is you're just going to take each edge, so say this top edge, and you're going to group it with its lower endpoint. Okay, and you're going to do this, for many of the edges. So for this one, we said its edges are its endpoints are 3 and 4. Let's group it with 3. For 3 and 5, let's group it with 3. For 1 and 5, we'll group it with 1. And we do this simultaneously for all edges. Okay, so now for every node, we have a collection of edges, and we're just going to run Dinkin's one uniform algorithm on each set separately. Okay. So does the algorithm make sense, I guess, before I start proving anything? Okay. All right, so first, let's also observe that this algorithm always accepts an acyclic subgraph. So remember, the edges or the elements in acyclic subgraphs are feasible. Okay, so let's prove this. So assume for contradiction that the algorithm somehow accepts a cycle. And let's let V be the earliest node according to the ordering that arrives in this cycle. Okay, then V has two edges in the cycle adjacent to it. And both of these edges have another endpoint that was later than V in the ordering. So that means that we have two edges from EV, because we defined both of these edges would have been put in EV by this definition. So this is a contradiction. Okay, so the algorithm will definitely never accept a cycle, so that's good. And now we want to prove that it gets a good approximation ratio.
What is arriving? The edges are arriving online, right?
The edges are arriving online, yeah. So the edges are ordered arbitrarily. It might be that you get some edges from node V and then some other edges from node V later. They're not ordered by nodes in any way.
It's a random order. The whole thing is a random.
The whole thing is a completely random order, yeah. Okay, so let's get some intuition for the algorithm first before proving that it works. Okay, so if we happen to get lucky and we choose an ordering that recursively selects leaves of the max weight spanning tree, then I claim we would get every edge of the max weight spanning tree with probability 1 over E. Okay, so in this example, let's say that the green edges are the max weight spanning tree, and we happen to choose the following ordering. Okay, so what do I mean when I say it recursively selects leaves? I mean 1 is a leaf in the max weight spanning tree, 2 is a leaf. Once 1 and 2 have been deleted, 3 is now a leaf of what's left, and then 4 is a leaf and 5 is a leaf once 3 and 4 have been deleted. Okay, so if you get lucky and you choose an ordering like this, what happens? Well, when we put the other edges back and we look at the partition we get, notice that every green edge is in a different partition. Okay, so this is kind of like the dream case, because now for each partition, we get at least the weight of this green edge over E. Here, we get at least the weight of this green edge over E, and so on. So, so by summing over each of these partitions, we're actually covering every edge in the max weight spanning tree with probability at least 1 over E. Okay, so this is what we would love to happen, but we don't know what the max weight spanning tree is ahead of time, so we can't choose this ordering. And the point is that we don't lose more than a factor of 2 by doing this randomly. Okay, so what's the proof? So let's first observe that the expected reward of the algorithm is exactly the sum over all nodes, the expected weight of the max weight element in EV divided by E. Okay, so this randomness is over the choice of EV, and this is just by saying when you run Dinkin's algorithm, you always get the expected max over E. Okay, so now let's let V be any leaf in the max weight spanning tree, and let E be the unique edge in the max weight spanning tree adjacent to V. Then we clearly have the expected max of, the expectation of the max weight edge in EV is at least WE over 2, because this edge E is in EV with probability 1/2. Okay, and we can do this simultaneously for all leaves, and think about it as once you pick a leaf, you pick this unique edge, and then you remove this edge in this leaf from the max spanning tree, and then you repeat. So now let's say V is some node that became a leaf in the max weight spanning tree once all the leaves were removed, and E be the unique edge in the max weight spanning tree adjacent to it. Then you can use exactly the same reasoning and say that the expected max weight edge in EV is at least WE over 2. Okay? And okay, so now you can just recursively repeat this reasoning for all nodes and all edges. And eventually, every edge in the max weight spanning tree is going to be covered by this reasoning by one node. Every node is going to be used here to cover at most one edge, because whenever it covers an edge, it's because it's the unique edge connecting it as a leaf. And so this implies that when you sum over all nodes of this expected max, you're going to get every edge is going to be covered by exactly one of these nodes by this reasoning, and so you get opt over 2. Yes?
I'm not following this. So if you have a node from which you have many leaves, and then there is a path above, and so once I remove these leaves, I mean, this node has a very low probability of, so one of these edges would be incident on.
Correct. So basically what I'm arguing is that maybe the expected max of edges in that EV, maybe it's actually way higher than the weight of this edge. But all I'm claiming is that I didn't use any of these edges. I covered these edges with the leaves that were touching them. So this node, maybe you do even better. Maybe you get whatever the max is of all the edges that are hanging off of it. But we don't even need that. You can pretend those edges aren't even there. You only get credit from the one left. Does that answer? Yeah. Okay. Are there any other questions about? Okay, so that's the complete proof. So this algorithm gets you a 2E approximation. And again, I want to highlight what is the underlying technique that might generalize. Is we decided to kind of decide that some feasible sets, even though they are acyclic subgraphs, we decided to call them not feasible. Okay, so we restricted the feasibility constraints. But we restricted them in a way that the new feasible sets were much simpler. Okay, so they happen to be a disjoint union of many smaller and simpler subproblems. But we did it in a consistent way so that any union of feasible solutions to the simpler problems is also feasible. So that was the first observation. Okay, so in this case, each subproblem was as simple as possible. It was just a one uniform matroid. And I just want to point out that many of these recent works follow this very similar high-level decomposition approach in the sense that they restrict what sets are considered feasible in this principled way. But the decomposition itself is more complex than this, and the subproblems that result are also more complex than this. But I just want to point out that this decomposition idea really does generalize beyond just graphic matroids. Okay? So is there any questions? So I'm going to move on from this result and do one last result and wrap up. So any questions about this? Okay. So the last result I want to show you is actually in a slightly different model called the free order model. Let me define for you what this model is. It's not very different. So still offline, every secretary has a weight chosen by an adversary. The adversary chooses feasibility constraints. And you'll notice what's missing is that the elements are randomly permuted. Okay, so what happens instead is you choose which secretary you want to interview one at a time. You learn their weight, and then you immediately and irrevocably decide whether or not to hire. And the rest of the problem is the same. You must hire a feasible set of secretaries at all times, and your goal is to maximize the expected weight of the hires. Okay, so I just want to make a note to convince you this is not like a cheating version of the problem, that if you restrict this problem to one uniform matroids, you get the original secretary problem back. Okay, so why is that? Because when you choose which secretary to interview, you don't know their weight, you only know the element. And in the one uniform case, all the elements are a priori identical. So you're basically choosing a random element that you want to interview. Okay? Okay, but that's just supposed to convince you that this is not like a crazy easy restriction. Okay, so I'm going to give one more definition. This is the last definition for the talk, and then I will state the theorem and prove it. Okay, so let's let S be any set and say that the elements are ordered in decreasing order of weights. And let J be the minimum index such that I is in the span of the first J elements. Okay, so what I mean by that is we're going to start with the heaviest element in S and go all the way down by adding each element one at a time. At some point, we will span I, and this is where we stop. And we'll say that the weight of the last element we added is equal to the price of I with respect to S. Okay? So does the definition make sense? So think of this as, so again, I'm going to start with the heaviest element and add one by one. Eventually, I'm going to span S. The weight of the last element I add to span S, I'm going to call that its price. Okay, so some examples is that for K uniform matroids, the price of I with respect to a set S is the kth highest element of S, because if I start with one element, I don't span I. If I keep adding, I need to have K elements, and then as soon as I have K elements, I span I. Okay, for a graphic matroid, the price of I with respect to S is going to be the min weight edge on the cycle formed by adding I to the max weight spanning tree. Okay, so again, the point is, when do I span I? I span I when I forms a cycle. What is the last edge that's going to be added before I have a cycle with I? It's going to be the min weight edge along this cycle. Okay, and just one observation that maybe will help with this definition is that I is in the max weight basis of S union I if and only if the weight of I exceeds its price with respect to S. Okay, so why is this? Because if I run the greedy algorithm to find the max weight basis for S union I will start with the heaviest element, and I will accept everything that is not spanned. So if I get to I before I span I, then I is in the max weight basis. If I get to the element that induces the price of IS before I get to I, then I span I. Okay, and the point is that I get to I before I get to this element if and only if the weight of I exceeds its price. Okay, so this is just some intuition for this definition. And now with this definition, we can state the theorem and state the algorithm that's used to prove it. Okay, so this is due to work of Jaye, Soto, and Zenklusen, where they showed that there is a 4 approximation for all matroids in the free order model. Okay, so what is the algorithm? So let's let this sample set S contain each element independently with probability 1/2. We'll process all elements in S first and reject all of them. And then we'll process the remaining elements in a specific order, in decreasing order of their price with respect to S. And we'll accept an element if and only if it's in the max weight basis so far and it's feasible to accept it. Okay, so everything about this algorithm is really simple, except for perhaps how do you choose this ordering? Okay, so let me just again give some examples of what this ordering would look like. So if the feasibility constraints are a K uniform matroid, once S is chosen, the span of the heaviest element in S is just the empty set because we don't span anything. The span of any set V is also the empty set if the size of V is less than K. But as soon as we get a set of size K, now its span is the entire ground set. Okay, so the ordering that this algorithm needs is actually just an arbitrary order. Okay, so what this algorithm would look like for K uniform matroids is it chooses this set randomly as described, and then the remaining elements can come in an arbitrary order, and the algorithm will still work. Okay. Here's a more combinatorial example where, okay, so graphic matroids, remember the edges are the elements, and acyclic subgraphs are feasible. So once S is chosen, let's say that S is the following 4 elements, and I1 has the heaviest weight. Then we're going to process the edges in the following order. So first, we'll process any copies of the edge AB, because this has because the price of these elements is I1, the weight of I1. Then we'll process any elements that form a cycle with I1 and I2. So these are elements who have both endpoints in the sets A, B, C, because their price is going to be I2. Then we'll process any edge with both endpoints in A, B, C, E, because their price is going to be I3. And then we process the remaining edges after. Sorry, so we get to choose the order of the elements. So when I say process, I mean pick that element to have its weight revealed. Yeah, sorry. Okay, so any questions about this? So this is, again, just to make clear what the algorithm is doing. I haven't tried to give you any intuition as to why it's good yet. Okay. Okay, so now there's, I'm going to give you one observation and then one proposition, and then we'll prove that the theorem works, the algorithm works. Okay, so first let's observe that element I is only accepted if its weight exceeds its price with respect to S. Okay, so why is this? Well, if it doesn't exceed its price with respect to S, then it doesn't exceed its price with respect to everything you've seen so far, and therefore it's not in the max weight basis so far. Okay, so we can only accept elements that exceed their price with respect to S. Okay, and now I want to reason the following. I want to provide a sufficient condition for it being feasible to accept an element I. So I'm claiming that if the price of I with respect to S is larger than the price of I with respect to S bar minus I, then it will definitely be feasible to accept I by the time we process it. Okay, so why is this? So first, by our choice of processing elements in the algorithm, all j that are revealed before I have a price with respect to S at least as large as the price of I with respect to S. So that was our algorithm's choice. Also, in order for any j to possibly be accepted, by this observation, its weight must be at least as large as its price with respect to S. Okay, so therefore, every element that is processed before I and is accepted has weight at least as large as the price of I with respect to S. That's just by chaining these two together. Okay, so now if it's infeasible for us to accept I, what must have happened? We must have accepted a set of elements that span I. Okay, but if that happens, then that means that we have a set of elements all in S bar minus I, whose weight is all larger than the price of I with respect to S. And this directly means that the price of I with respect to S bar minus I is larger than the price of I with respect to S. Okay, let me go through this last sentence one more time. So remember that the price of I with respect to S bar minus I means I start with the heaviest element in S bar minus I, and I keep going down, and I stop when I span I. Okay, and we know that we can span I using elements that are all heavier than the price of I with respect to S. So that means that this process definitely stops before we have considered any elements with weight lower than the price of I with respect to S. This directly means that the price of I with respect to S bar minus I is at least as large as this. Okay? So this is actually really the key lemma in driving the proof. Okay, so now the rest is just finishing up and showing that basically that this happens with good probability. Okay, so here's the rest of the proof. So I is in S bar with probability 1/2. That's by choice of S. Independently, the price of I with respect to S is larger than the price of I with respect to S bar minus I with probability 1/2. And that's because of how we chose S, that S and S bar minus I are equally likely to be flipped. Okay, so the price of I with respect to S is larger than the price of I with respect to S bar minus I with probability exactly a half. And for any I in the true max weight basis, it will definitely, we will definitely accept I whenever both of these occur, because this means it's feasible to accept I when it arrives. And this means that I comes in S bar, so it's not part of this rejected set. And so this directly says that we accept every element in the max weight basis with probability at least a fourth. And that gets the 4 approximation. Okay, so that's, so you can ask, so are there any questions about this proof? So I'm just going to say one sentence and then just wrap up the talk. Okay, cool. So what is the underlying technique here that might generalize? Well, so basically we showed that you can couple good samples, ones that result in it being feasible to accept I, with bad samples, ones that result in it being infeasible to accept I, in a way so that whenever S is bad, then S bar is good. And that let us bound the probability that it's infeasible to accept I. Okay, so now I'm going to start summarizing and wrapping up. So what we saw was 3 different algorithms. We saw an E approximation for K-uniform matroids. And the main idea behind this algorithm was that we found a clever way to charge a different element in the max weight basis of the samples for everything we accept, and we did this in a consistent way. We saw a 2E approximation for graphic matroids, and the main idea was we made stricter feasibility constraints that decompose into much smaller and simpler, subproblems. And we also saw this 4 approximation for matroids in the free order model, and the main idea was to try and couple these good events with the bad events in a way to show that the bad events don't happen too often. Okay, and again, this is not supposed to be an exhaustive list of every high-level technique that can be used to design secretary algorithms, but I do think it's a pretty good sample of some of the good high-level ideas. Okay, and so again, I want to do similar to before, just touch on a couple of results in very related models. So what if the objective function isn't linear in the weights? So what if you're not trying to maximize the sum of weights, but you have some submodular set function, and your goal is to try and maximize f of whatever set you accept? Okay, so there's been a ton of works showing constant factor approximations for various different kinds of matroid constraints. And I want to point out one of them separately. There's recent work of Feldman and Zenklusen that shows a generic reduction from the submodular secretary problem to the linear secretary problem. So if you can design good secretary problems for the linear objective, you can plug that into their reduction and get a good secretary algorithm for any submodular function as well. Okay, here's another change twist on the model is what if the adversary gets to choose the weights and the feasibility constraints, but he doesn't get to choose how the weights are mapped to the elements? Okay, so what if the weights are randomly assigned to the elements? Then in this case, it makes it harder for the adversary to generate hard instances. And in fact, we know that in this model, for all matroids, there is a constant factor approximation, even if the adversary gets to choose the ordering. Okay, so the point is that really why the matroid secretary problem is so difficult is exactly because the algorithm can choose how to assign the weights to the elements. Okay, and another question you might ask is what if the ordering is not completely random? Okay, so we know that you need some randomness to possibly get any bound, that completely worst case ordering is hopeless. But it turns out that you actually don't need all of the entropy of a uniform random order in the single choice case, that actually like exponentially less entropy suffices. Okay, so this is just one slide of some of the current directions that people are studying in these problems. So the obvious question is there a constant factor approximation for all matroids in the standard model? Okay, and I'll point out, in my opinion, I think the most interesting special case that hasn't been resolved yet are representable matroids. So here, what I mean is pick your favorite field. Is there a constant factor approximation for the matroid secretary problems for all vector spaces over that field? So this we don't know the answer to yet. And again, if you don't remember from the slide, the best approximation we know for general matroids is the log of the rank. Okay. Also, my own opinion is I I personally get excited whenever we prove tight E approximations for any special cases. And currently, we really only know this for transversal matroids. We don't know a tight E approximation for graphic matroids, for laminar matroids, or for all matroids in the free order model. Okay, and also, I think depending on who you ask, some people believe that really the right answer for all matroids is E. So maybe it's not possible to prove a lower bound of anything larger than E for arbitrary policies. But maybe there's some interesting lower bounds proving, say, that an algorithm, certain kinds of algorithms can't get a tight E approximation. Or maybe algorithms with proofs that look like ones we saw can't get an E approximation. Okay, so that's everything I have. Thanks again for listening.
Look like this is also a good question.
All right, thanks.
So what's